So these notes define what simplified exponent form is really about. As you go through, basically we have to have some unified way of describing what do we consider simplified so that everybody's work will come out looking the same. And so mathematicians defined this way, and so it's fairly universal. That all of those four facts need to be true about an expression for it to be considered simplified. So as you take a look down this list, we actually know how to deal with most of this, but actually not all of it. The first line, all exponents are positive. Remember, that means we can't have a negative exponent in there or a zero exponent, because remember, anything to the zero is 1. And actually, that's good to make note of here in case you've forgotten that. Anything to the 0 equals 1. But what happens with the negatives? This is one of the most commonly forgotten ones, so it's also worth reminding us. If I have x to the negative anything, I'm going to call it n. X to a negative exponent equals 1 over x to that positive power. So that's how I get rid of the negative there. Or if it's already in the bottom, 1 over x to the negative n. Again, I flip it in the fraction, so in that case it would end up on the top. So the negative exponents, remember, flip whatever it is in the fraction, either top to bottom or bottom to top. And by flipping it, it makes the exponent positive. So that's how we deal with the first one there. All exponents are positive. No fractional exponents. That's the one we just have been dealing with so much recently, where we can see that x to the a over b equals the b root of x to the a. So we avoid any fractional exponents by turning them into radicals. The third one, no radicals in the denominator. This is where things get a little bit tricky, because if I give you something like 1 over the square root of x, we have to get the square root out of the bottom of that. Well, and that's going to be the next thing we talk about, so save that one in mind. And then no parentheses, well, yeah, that just means, if there's any multiplying to do within it, so like if I have x to the a times y to the b all to the power of c, it just means I turn it into x to the ac and y to the bc. I do each of those to that same exponent. But this radicals in the denominator thing, we got to take a look at that. So here's our basic one, 1 over the square root of x. And it just says simplify. And remember, simplified exponential form, simplified exponent form is what we were just noting, so I got to get the radical out of the denominator. Well, there's a nice little trick for that. What gets rid of a square root? Squaring it. Okay, well, I can't just square the top and the bottom. I can't just do that, because that would no longer necessarily equal the same thing. I'm going to go off on a little bit of rabbit trail here. If I did 1/3 squared, so if I took that and I squared both the top and the bottom, that would equal 1/9. It doesn't equal the same thing anymore, right? Whatever I do to this fraction, it still has to equal the same value. I'm just changing the form. So squaring something, remember, means to multiply it by itself. I can then do that. I can multiply the square root of x by itself on both top and bottom. Because remember, if you multiply the same thing into both top and bottom of a fraction, it still equals the same thing. Because technically I could cancel those out. It's just I don't want to cancel them out because it's going to help us here. So that's what we're showing here. I'm multiplying top and bottom of my fraction by root x. When I do that, then on the top, 1 times the square root of x is just the square root of x. On the bottom, the square root of x times the square root of x equals x. Because if I multiply it by itself, that means I'm squaring it. And we already know that squaring a square root cancels out the square root. Now, if I want to show this the long way, why does it cancel it out? I actually want to show you this because it's going to be relevant to work you're going to be doing further. Square root of x times square root of x, remember that equals x to the 1/2 times x to the 1/2. And if I do that, I'm adding the exponents, so that becomes x to the power of 2 over 2 and the x to the power of 2 over 2 is x to the power of 1, which is just x. So that's why it works from another angle, and seeing why we can actually get away with doing that. But the general idea here is that anytime you have a square root in the bottom of your fraction, multiply top and bottom by that square root. All right, so we're now going to apply that same idea to these two problems. So write down both, and if you feel confident about how to proceed with them, go ahead and go with it. If not, write them down and start thinking about how it compares to the previous one, but go ahead and hold up there because we'll walk through it together. All right, so let's see how we would approach them. So this 4 over root 3, again, I can simplify it further because right now I have a square root in the denominator. I don't want to leave it that way. So to get rid of the square root in the denominator, that means I got to multiply it by itself. So I'm going to multiply it by root 3. And whatever I multiply into the bottom of the fraction, I also have to multiply into the top. So we multiply top and bottom both by root 3. Well, on the top, if I do 4 times root 3, that just gives me 4 root 3. On the bottom, if I do root 3 times root 3, remember that's the same as square root of 3 squared, so that's why it's just 3. Well, I can't do anything to simplify the top, the 4 root 3, because the square root of 3 doesn't simplify. And the bottom's just 3. I can't reduce anything with the 4 over 3. Oh, and in case you're wondering, can I reduce that because there's a 3 in both? No, because the top 3 is inside of a radical and the bottom 3 isn't. So that top 3 isn't really a 3. It's the square root of 3, which is some ugly decimal, so I can't cancel it with a whole number 3 on the bottom. So yes, that's as good as it gets. That's your final answer. All right, for the second one, I again have a square root in the denominator and I can't leave it in the denominator. So we need to multiply that denominator by itself, that is by the same square root. So I'm going to multiply it by root 5x. And if that's what I multiply the bottom by, I got to do the same on the top. So that's also a root 5x. All right, so now when we go ahead and multiply that, on the top that just gives me 20 times the square root of 5x. So I can just write it as 20 root 5x. Over. Now on the bottom, the root 5x times root 5x, I'm squaring it basically again. So the square root goes away, I'm just left with whatever was inside, so that gives me 5x. All right, so then, am I done? No. Because my result can actually reduce a little bit. Because I see here that the whole numbers, the 20 and the 5, those are the only parts I can consider when it comes to reducing. Yes, those will reduce. What does 20 over 5 equal? 4. Yep, just 4. If you prefer to think about it as 4 over 1, that's okay to help get your head around this. So that means I now have a 4 on the top. The root 5x was unchanged. On the bottom, the 5 just canceled out. And so I'm just left with x. So that now is our final answer. Effectively, what I did is I now divided top and bottom by 5. That's what our actual reducing is doing there, is dividing top and bottom by the same thing. So that's why we get the 4 on top and just an x on the bottom. All right, so next up we're taking a look at simplifying these radicals. And we're going to actually take this someplace. So simplify each of these on your own first. And remember the general strategy is what we're doing is we're looking for the biggest perfect square that goes into each number. And so the square root of 200, the biggest perfect square that goes into that is 100. And it goes in 2 times, so I always want to start by writing it that way. And then we can actually take the square root. So square root of 100 gives me 10. And so it's 10 root 2. And we do the same thing for the others as well. This is what you should have found for each of those. So go ahead and check your answers there. Now, we're going to take those same skills we used to do that set of 3 problems to do this 1 problem. I've purposely given you the same roots so that we can save ourselves a little bit of effort here, but here we're adding and subtracting radicals. And so now you can go ahead and just put in the minus and the plus in the problem that you did before if you wish. Because when we are adding and subtracting radicals, We actually got to do a little bit of work first before we can actually do the addition and subtraction. Because, like, if I'm adding fractions, I have to have a common denominator because I have to be adding the same thing together, right? If I'm adding variables, they have to be like terms, so that we're actually talking about the same things. The same thing happens when we're talking about radicals here. We have to be talking about the same radical that's involved. So step one for each of those three radicals that's involved in the problem, I simplified. Well, that's why I had you already do that simplifying. So this is what our problem then looks like. It's just that instead of three separate problems, it's a single problem where we're subtracting and then adding them. But now that we've gotten to this point, now I can actually do that subtraction and that addition. Because you'll notice that now instead of a whole bunch of different radicals, I now have three of them that all involve root 2. Now if one of them did not involve root 2, like if this one was a root 3 instead, I would not be able to add that one with the others. I can only add the ones that have the same radicals. All right, and so then we can go ahead and add and subtract them just because they're like terms. So I have 10 root 2's, and I take away 5 root 2's. Okay, so that leaves me with 5 root 2's. And I still have to add the 3 root 2's to that, so that gives me a grand total then of 8 root 2's. Yeah, so my answer there is 8 root 2. Now the big thing to notice here though is that I really did have to do that simplifying of the radicals before I could actually do that addition and subtraction. Some people end up wanting to try this method down here. Just to prove to you why it doesn't work, if I did 200 minus 50 plus 18, that'd give me 168. The square root of 168 does not simplify down to be 8 root 2. They're completely different numbers. So, no, it doesn't work to just do it that way. So the other type of new problem that we're doing today is this, where we're actually multiplying with radicals in there, specifically multiplying binomials with radicals. Well, the basic principle behind it all is the same as it always has been. I'm going to multiply everything in the first parentheses by everything in the second parentheses. It's just that when we have the roots in there, we're just going to have to see what that does to our answer. So let's go ahead and just start running through that. So I'm going to do 5 times 7 first, so that gives me 35. Then I'm going to do 5 times the 2 root 3. All right, now it's positive, so it's going to be a plus. When multiplying these two, I just do the 5 times the 2. The stuff that's outside the radical, I multiply the stuff outside. So 5 times 2 gives me 10. The stuff that's inside multiplies by stuff that's inside. In this case, since there's only the 1 root 3, it just stays root 3. So 5 times 2 root 3 is 10 root 3. Okay, makes sense, hopefully. All right, now I'm going to go over to the root 3 multiplied by both. So root 3 times 7 is 7 root 3. And then the root 3 times the 2 root 3. Now again, anything that's outside of it stays outside of it. So the 2 stays outside. But then I have to multiply root 3 times root 3. And there's two different ways that people think about it. Some people are just going to say, okay, it's the square root of, now go ahead and multiply the stuff inside. 3 times 3 is 9. Or some people, instead of writing it as 2 root 9, they'll just say, oh, well, root 3 times root 3. A square root times itself equals whatever's inside, so it equals 3. So you might also have written that line as 2 times 3. Those two, either would be a good way to put your work in there. It all just depends on how you're choosing to think about this. But you should know that they're both equivalent at least. Now, if you didn't start by writing that as 2 root 3, on your next line you will need to put it as 2 root 3 because, or I'm sorry, 2 times 3. Because we're going to actually now have to combine some like terms. So I'm going to do 35 plus, let's see here, I can go ahead and combine the 10 root 3 and the 7 root 3 here. Because remember in that previous work, if the roots are the same, I can add them, so that gives me 17 root 3. Plus 2 root 9, or 2 times 3, that just equals 6. So then I have one more step to go here. I got to do the 35 plus the 6, so that gives me 41 plus 17 root 3. Can I add those together now? No, they're not like terms. That is, one involves root 3 and the other one doesn't. Just like if I had 41 plus 17x, I couldn't add them. Same kind of thing here. So that's your final answer. Next up, we're going to be dealing with really big, ugly looking things. And how do we handle things that look really complicated like this and actually make it work? So go ahead and write down this problem, then we'll walk through it together. Now, we've done problems like this in the past. We saw one before where we had kind of shortcut the process by writing a single root over the fraction, then just simplifying the fraction. Can I do that in this case? No. Because what root would it be? Would it be the square root from the top, or would it be the cube root from the bottom? They're different. And so when the top and the bottom are different roots, we can't just write the entire fraction under a single radical. Okay, so what do we do instead? Well, we can go ahead and simplify the top and the bottom separately. So go ahead and simplify the top of this and simplify the bottom. And then we'll just go from there. And so the basic process of simplifying it is the same as what we've been doing recently, where we start by turning each of those into a fractional exponent, and then we simplify each of those terms from there. So for instance, like my 12 over 2 here is going to become just x to the 6th, and so on. And so when we just do that simplifying process, this is then where it drops us off. So on the top I got x to the 6th, y to the 4th, z, and then a square root of z. Because remember that z to the 3 halves, that's z to the 1 1/2. And so I end up with z to the 1, of course I don't have to write the 1 in, times z to the 1/2. And z to the 1/2 is square root of z. All right, then the same thing on the bottom. I simplify each of those fractions. Thankfully on the bottom they all give us whole numbers. Makes our lives a little easier. Because remember, if I ended up with a square root on the bottom, I'd have to get it out of the bottom, because I can't leave a square root in the denominator. All right, so now we can go ahead and simplify from there. So I basically am now just going to look at each of the different letters and reduce those terms, like x to the 6th over x squared. 6 minus 2 is 4, so that gives me x to the 4. And then repeat the process with the y's and with the z's, reducing as we go. And you should find that in this case, everything on the bottom cancels out, leaving something on the top. The top was definitely the bigger side in this case, so there's no more fraction left in that case. If the bottom numbers were bigger, well then we'd still just have a fraction with some of those terms on top and some of them on the bottom. Having done that problem, I think that you can then go ahead and tackle this problem. So go ahead and try doing this one entirely on your own, and then we'll come back together and see how it all ends up working out. All right, so when we just simplify the radicals and reduce our fractional exponents and all that kind of stuff, this is what we end up with. Now we're at the point of reducing the fraction itself. So now we can start looking, seeing what's in both the top and the bottom. But in this case, notice things like the a over a to the 4th. That means we got more a's on the bottom. So my answer is going to have a in the bottom, specifically 3 of them. Because 1 minus 4 is a negative 3. That tells me the 3 goes in the bottom. Remember, a negative exponent flips it into the bottom, or flips it from the bottom to the top. All right, then we repeat the process with the b's and the c's. And you notice we end up with this, which is looking pretty darn good, but it's not totally simplified yet. Because remember, we cannot leave a square root in our denominator. So then, how do we get the square root out of the denominator again? Well, remember, we multiply top and bottom by that square root. So I'm going to multiply top and bottom in this case by the square root of b. It's called rationalizing the denominator. All right, so if I multiply top and bottom by root b then, that ends up giving me this. Notice the root b on the bottom, when I multiplied it by itself, just became a b. But now this is no longer a simplified fraction. It's no longer a reduced fraction, because now you'll notice that because I just freed up that b on the bottom, I can now go ahead and reduce it with that b on the top. Notice it's the b that's outside of the radical on the top that I can actually simplify it with. So last step, I reduce those b's, and this is what you're then looking at as your final answer. B cubed times the square root of b all over a cubed times c.